Okay, we will start this over. Do you see the screen now?
Yes, sir.
Okay. So again, we continue with the Steel Bridge from Concept to Delivery lecture series. Uh, Last time we looked at the bridge infrastructure, the steel bridge industry, and bridge steel, and we also looked at the infrastructure condition and replacement needs. And today we're going to go through the short span steel bridge, steel girder bridge economics, and E-span 140. So what Lecture 2 does is it presents a direct initial cost comparison between steel and concrete short span bridges. The purpose is to address the preconception that concrete is always less expensive than steel for short span bridges. The lecture continues by examining the life cycle costs of typical steel and concrete bridges in the state of Pennsylvania. The presentation concludes by demonstrating a free short span steel bridge design tool called E-span 140 so that engineers can produce a steel design in a matter of minutes instead of hours. Using E-span 140, the engineer can quickly and directly compare a steel bridge and a concrete bridge side by side. As mentioned in Lecture 1, the Alliance was formed to address two main concerns with the construction of steel bridges. The first is a misconception across the United States that for shorter span bridges, concrete is always less expensive than steel. The second issue is that a concrete bridge is easy to design using charts and tables, whereas a steel bridge design is an individual piece of art for each design project. Lecture 2 will look at initial cost case studies for county and state bridges to show that competitiveness of steel and to demonstrate that life cycle costs for steel and concrete bridges are also competitive. We will finish with a presentation on E-span 140, an online tool for preliminary steel bridge design for simple span bridges up to 140 feet in length, so that steel and concrete bridge alternatives can be compared easily without an undue and costly design for the steel bridge. We start with the preconception that concrete bridges are less expensive than steel bridges in the short span market. Many owners and engineers across the country believe this to be true, and many times steel is not even considered when there is a short span bridge need. This is unfortunate because that means owners may be paying more for their bridges than is necessary. If owners and engineers would compete steel and concrete bridges, the cost for both would be lower due to the competition. Studies show that states or regions that do not even consider steel alternatives and only build concrete bridges pay more for those concrete bridges than states or regions that have a healthy competition between the two bridge materials. We will now look at case studies of county and state bridges. The first case study is from Audrain County, Missouri from the year 2012. These two bridges were built by an Audrain County work crew, so there is no contractor for these two bridges. This is a special case study in that the Short Span Steel Bridge Alliance worked with the county engineer from before construction through the opening of the bridge to track all of the costs. The steel bridge, or Missouri Bridge 411, consists of 4 steel girders, a 47.5-foot span, a 24-foot roadway width, and a 2-foot structural depth. The concrete bridge, Missouri 336, consists of 6 precast hollow core slabs with a 50.5-foot span, a 24-foot roadway width, and a 2-foot structural depth, just like the steel bridge. These two bridges were built in the same year and are nearly identical except for a small difference in the span length. The engineer was asked to keep a detailed account of the cost for the construction of the two bridges so that a direct comparison could be evaluated. This shows the total cost of the two bridges where the costs are broken into material, labor, equipment, guardrail, rock, and engineering. We can see that for the total cost of these two bridges, the steel bridge has a 19.3% savings over the concrete bridge. The total cost for the steel bridge is just under $112,000, and the total cost for the concrete bridge is just over $154,000. However, since one is just a little bit longer, the way we can compare bridges is to divide by the area of the deck surface. And if we do that, the steel bridge comes out to be 97.5 bucks per square foot, and the concrete bridge comes out to be $120.83 per square foot. However, comparing only total cost can be deceiving given the different site characteristics of the two bridges. For instance, we see here that the concrete bridge had significantly higher engineering costs at over $21,000 compared to the steel bridge where the engineering costs only cost about $8,200. We also see a difference in the cost for the rock, which does not have to do with the structure, but is the rock that is put along the stream bed to protect the bridge. So to address these differences, the engineering and the engineering plus rock costs are removed from the total cost to get a better comparison between the two bridges. When the engineering and rock costs are removed, the concrete costs about 98 bucks a square foot, whereas the steel bridge had a cost of 83, or a 15.4% reduction in cost for the steel bridge. However, there are still different site requirements that may influence the difference, such as roadway alignment work, approach work, grading and finishing, and other work for the two projects. So the engineer that worked with the Alliance was also asked to separate out only the superstructure costs so that an equivalent direct comparison could be made for the two bridges. These costs represent the costs associated with only the superstructure. This is a true apples to apples comparison of the cost for these concrete and steel bridges. Removed from the total costs is all site prep work, grading, engineering, rock, abutments, and so forth. We can see that the steel structure is made up of the girders, which are kind of expensive, the deck panels that are used for forming the deck for placing the wet concrete on top of, the reinforcing in the deck, the concrete for the deck and the abutments, the labor costs from the county crew that built it, and the equipment costs. The concrete is divided up into the slab girders, which is pretty much the total bridge. They just lay those down, so there are no deck panels. There is some reinforcing steel in the abutment work, the concrete for the abutment work, the labor, which is pretty close to the steel and the concrete, and the equipment, which is significantly higher. So we can see the cost for the materials, labor, and equipment for only the superstructure. The steel bridge costs 37.5 bucks per square foot, and the concrete bridge costs about 50.5 bucks per square foot. The steel bridge is considerably less expensive for this comparison. So I say this is a true apples to apples comparison because we can almost pick up the superstructure from one of the bridges and place it on the other abutments of the other bridge. Now there's a little difference of 3 feet, but they are almost identical bridges. Now, one item to note is the equipment cost, where the steel bridge used a county-owned 30-ton crane. The concrete bridge girder members are heavy, and the county had to rent a 100-ton crane at a cost of $3,500. The other $500 for each was a rented skid steer for the incidental work it takes to put a bridge together. However, even if the county needed to rent that 30-ton crane instead of having it being owned by the county, the cost would be about $1,520, and that increases the steel cost to only $38.88 per square foot, still considerably less than the concrete bridge. For the steel bridge, the steel girders are weathering steel that requires no painting, and these costs are already in the cost of the steel girders, as shown here. If the county needed additional corrosion protection, for instance, if weathering steel was not applicable, and they used galvanizing, the cost for galvanizing is about 22 cents per pound, which would add money to the cost of the steel bridge, but the total cost would still be significantly less than the concrete bridge cost. So for these two bridges as they were built, the superstructure only costs show that the steel bridge option would have a savings of over 25% compared to the concrete bridge. That means that you could build 5 steel bridges for the cost of 4 concrete bridges. This is for 2 almost identical bridges where they have the same structural depth, which means no difference in the approach work, the same roadway width, the same guardrail system, the same abutments, and the same county crew built both bridges. This demonstrates that steel is competitive with concrete, and the preconception that concrete is always less expensive is incorrect. Steel short-span bridges can, and many times will, be less expensive than the concrete option. The reason for these economies for steel bridges vary over the bridge fabrication and the construction process. For instance, we saw that one reason steel is competitive is that equipment requirements are less since steel bridge components are considerably lighter than the concrete components. For steel bridges, the dead load is significantly lighter and lighter abutments can be used, or some of the economical modular abutment systems can be employed, such as geosynthetic reinforced soil systems, at much less cost than the heavier concrete abutments. Another benefit for the economy of steel bridges is the use of partial depth precast panels or corrugated metal deck systems that make the casting of the concrete deck efficient. We talked in lecture 1 that steel is a versatile material and that steel bridges can be made in many forms with complicated details and fabrication. However, for these simple bridges, they do not require complicated stiffener and diaphragm details. Simple details like shown here, which is just a channel diaphragm, are cost-effective and easy to fabricate and easy to erect, which cuts costs. Another costly component for bridges are rocker or pot bearings at the end of the girders. For these simple bridges, simple elastomeric bearings can be used and smaller bearings used due to the lighter weight of the structure. Also, jointless decks with integral abutments, as shown here in the picture, leads to much lower deterioration rates and maintenance costs in the future. Finally, one of the costs for steel bridges is corrosion protections, since regular steel rusts. However, weathering steel, when applicable, is a low-cost protection system and requires little maintenance for long-term corrosion protection. If weathering steel is not applicable, galvanizing, metallizing, painting, or the use of stainless steel may be a cost-effective method for corrosion control. And we'll talk about these durability and protection systems in lecture 4. So that was one example. That was one case study comparing 2 bridges. The Alliance also worked with the county engineer on other bridges built near the same time frame. This table looks at the total constructed costs of an additional 5 steel and 4 concrete bridges built in Audrain County. At the bottom of the table, we see that sometimes steel is less expensive and sometimes concrete is less expensive. This is healthy competitiveness and is good for the owner. These are examples of county bridges that show that both steel and concrete are competitive in the short span market, and both should be considered. Not shown here due to time, the Short Span Steel Bridge Alliance has many more similar examples. These examples were county-owned bridges. Next, we will look at a couple state bridges still in the state of Missouri. Here are 2 nearly identical state bridges, one steel and one concrete, that cross over the same highway near Columbia, Missouri. Both are 2-span with the concrete bridge just a little longer and wider. So again, the total cost will be divided by the deck area for comparison. These are both design, bid build projects with a contractor constructing the bridges. Here are the costs for the two bridges, with the concrete being on the left and the steel being on the right. Both had non-bridge items such as conduit systems, a pedestrian fence, and an architectural facade on one of them because it was kind of an entrance bridge into the city. And these costs were removed, shown here in green, from the total cost since they are not structural components. We see that the concrete bridge has a cost of $77.71 per square foot, and the steel bridge comes in at $72.94. However, the concrete bridge was built in 2011 and the steel bridge was built in 2007, and that 5-year difference does have an impact on cost due to inflation. To account for the age difference and inflation, the Engineering News Record Construction Cost Index of 2.7% per year was used to bring the costs of both of these two bridges up to a common year of 2017. We see that the steel bridge was the lesser cost at $85.58 per square foot, and the concrete bridge came in at $91.18 per square foot. From what we have seen here, and with many more examples not shown here, we see that steel is competitive with the concrete bridges in the short span market, and that owners and engineers should consider both materials for their bridge needs. That preconception that concrete is less expensive than steel in the short span market is a misconception. Both steel and concrete is competitive, and competition is good for the owner and the public. But first cost is just that, the cost of putting the bridge in place. Responsible engineers and owners are concerned about future maintenance costs and life service costs and service life. The question about life cycle costs routinely comes up, while what is actually asked is which type of bridge is best for life cycle costs. And both steel industry and the concrete industry offer anecdotal evidence, but has not, until now, had good evidence on which bridge type is best. So a study was conducted that examines the historical life service, meaning performance and maintenance, and agency life cycle costs, meaning the true cost for the building and maintaining the bridge over its life, of steel and concrete bridges in Pennsylvania. A historical study was conducted so that the results show what actually happened to the bridges instead of anecdotal guesswork from the steel and the concrete industries. The Pennsylvania DOT had good records on their bridges and offered the PennDOT data for the study, and we want to certainly thank them for that. So, to determine a life cycle cost for a bridge, one needs to know the full history of that bridge. This includes the initial costs and the year it was built, and all maintenance that occurred over the life, including departmental maintenance and contractor maintenance, and the lifespan of the bridge, or when it will be replaced. Of course, all of the bridges in the PennDOT database were still in service. So an end-of-life model is needed to estimate the life of the bridge, as we'll see in a few slides. The study's objective was to compare life cycle costs of typical concrete and steel bridges. So there were criteria that each bridge had to meet to be included in the study. The criteria included considering only typical steel and concrete bridges, where that was defined as precast I-beam, precast box where the boxes were adjacent to each other, precast boxes where the boxes were spaced apart from each other with a concrete deck slab, steel rolled beam bridges, and steel plate girder bridges. In addition, both precast concrete became a mainstream construction method, and modern steel design and detailing started in about 1960. so it was limited to bridges that were built after 1960 and before 2010. Each bridge that was used in the database had to have complete records for initial costs and date built, and accurate dates and costs for any type of department or contractor maintenance. And since the study was looking for typical bridges, it removed any bridges that had exceedingly high or low initial costs. And all the costs that were used in the life cycle cost study were those recorded in PennDOT references. So starting out, PennDOT has over 25,000 bridges in their database. Of those, almost 8,500 are of the 5 types considered in the study. And of those 8,500, over 6,500 were built between 1960 and 2010 for a potential study database. When these 6,587 bridges were subject to the criteria, many of them did not have accurate and complete life history information, which left a database of a little over 1,700 for the life cycle cost study. This is over 25% of the potential bridges represented in the life cycle cost study, which is a pretty good representation. All of the 1,700 bridges are still in service, so a bridge life model needed to be developed to predict when the bridge would be taken out of service or replaced. The model is based on the inspection superstructure condition rating that occurs at least every 2 years, and that condition rating varies between a number of 0 and a number of 9. 9 being a perfect bridge, usually associated for when it was built, and 0 being a bridge that has collapsed. It was assumed that the bridge had a rating of 9 when it was built. A deterioration rate was determined based on the condition rating in the year 2014 by the change in rating divided by the years. The change in rating from when it was built to the condition rating in 2014 divided by the years of service so far. With the deterioration rate, the remaining life can be estimated by assuming the bridge would be replaced when the superstructure condition rating became a 3. And the bridge life is the sum of the remaining life added to the current age. So this table shows the first results from the life cycle cost study. It shows the average deterioration rates for the 5 types of bridges for not only the 1,700 bridges in the study, but for the over 8,500 in the potential bridge numbers. For this presentation, when these results tables are shown, there will be 2 aspects of the results. The first one is shown down here on the bottom right. First, the top 2 best performance types of bridges will be highlighted. For instance here, steel rolled beam bridges have the lowest deterioration rate at 7.1% of a condition rating per year, and the precast spread box bridges is second with an 8% deterioration rate. The second aspect is this statement here on the bottom left, where it says all bridges are similar with none way out of balance. What this means is that there is no one type of bridge that greatly outperforms the others, nor is there a type that is significantly less than the others. I will address this statement, all are similar with none way out of balance, towards the end of this presentation. We will look at the life cycle, we will look at a life cycle analysis of an example bridge to demonstrate the work of the study. This bridge is a precast spread box bridge built in 1969 with 3 spans and a deck area of 7,600 square foot. In 2014, the base year of the study, the superstructure rating was a 5. Knowing the average deterioration rate for spread box bridges is 8%, the estimated remaining life when the condition rating reaches a 3 is 25 years. Given that the bridge is 45 years old, the predicted lifespan for the bridge is 70 years. The top of this slide shows the actual years and costs for the initial construction and all the maintenance over the lifespan. Just like with the case studies, the actual costs are divided by the deck area for comparison to other bridges. To compare life cycle costs over the database, inflation has to be taken into consideration. So all of the bridges were assumed to be built in 2014, and all of the costs inflated by that engineering news record construction cost indice, like we saw for the earlier case study. So this bridge in 2014 dollars would cost $143.45 to build, and the maintenance costs at year 19, 40, and 44 would have these associated costs in constant 2014 dollars. The study uses constant 2014 dollars for all future costs since the discount rate considers inflation for the future. So now we're ready to develop the life cycle of the bridge with dates and costs in 2014 dollars. Using a discount rate from the Federal Office of Management and Budget of 2.3% that takes into consideration inflation of the future 2014 dollar costs, a present value cost, just like you did in Vista 2, of the bridge's life cycle can be determined to be $154.49 per square foot by discounting the future costs back to the year of 2014. This means that if $154.50 per square foot was put away when the bridge was built, the amount could pay for the initial costs and all future costs for that bridge cycle. However, we cannot compare the present value cost of a bridge that lasts 70 years to a bridge that lasts only 40 years because the outcomes are not equal. A way to compare different life cycle bridges is to use perpetual present value costs, also called capitalized costs, by assuming that the bridge is replaced after each cycle in perpetuity. For this bridge, the capitalized cost is $194 per square foot, or just shy of that. Which now, what that means is that that amount was put away today. It could pay for the first cycle bridge and replacement of that bridge every 70 years forever. If we put all of the bridges into capitalized costs, we can now compare all of the bridges in the database directly. And so that was what was, additional bridges were removed based on the capitalized costs. Because again, this study wanted to look at typical bridges. So in the database, the bridges within plus or minus one standard deviation of the overall average was kept as the study bridges. This left almost 1,200 bridges of the 5 different types that were used to study the results. So with these about 1,200 bridges, a database was organized by bridge type in 3 Excel worksheets for each type. The first worksheet was the bridge information with location, year built, number of spans, bridge length, deck area, geometry, and bridge materials. The second was the department and external contractor maintenance performed on the bridge with costs and dates. And the third was the initial and the life cycle cost results. The studies and the final report was produced from this database for the 5 different types of bridges. The report considered bridge life and capitalized costs, where the capitalized costs were studied for several variables as shown here. Total capitalized costs, dependent on number of spans, dependent on bridge length, looking at the present value costs of only the future costs, looking at the present value costs of department maintenance, looking at present value costs of external contracts. Here in Lecture 2, we will look at bridge life, capitalized costs for the entire database, and then capitalized costs for short-length bridges, as shown in blue here. But the full detailed report can be found at www.shortspansteelbridges.org, the host website for the Short Span Steel Bridge Alliance, as we talked about in Lecture 1. And then after this study was completed, an additional study was performed to look at the life cycle costs of galvanized steel girder bridges. And that report can also be found at the website. So the first one we're going to look at is bridge life. For bridge life, the database of the 5 types of bridges show that the rolled beam bridges have the longest predicted life at over 81 years. And the second was the precast spread box bridges at just under 80 years. However, we see that statement at the bottom left that say all are similar with none way out of balance. And that is true here. None of the bridge types varied much from the others with a 7-year spread. And at the bottom is that, and we will deal with that statement later in the presentation. Now, a good way to look at predicted life that considers not only the average life, but also the standard deviation of the life is a statistical cumulative density function, or CDF. Here it is assumed that the data is normally distributed, and with the CDF, the question can be asked, what is the probability that a type of bridge will last at least 75 years? 75 years is the expectation for modern bridge construction. The results show that there is a 73% chance that a rolled beam bridge will last at least 75 years, and a 65.6% chance that a precast spread box bridge will. However, it also shows, according to the data of this database, there is only a 44.3% chance that a precast I-beam bridge will last 75 years or more. This is a good information for both engineers and bridge owners. So now we're going to move on to capitalized costs, or the perpetual present value. And this table shows all the bridges in the database. Here we see that the precast I-beam bridge has the lowest capitalized costs, and the steel rolled beam bridge is second. The table also shows the initial costs, the initial costs, the present value costs of future maintenance, the average length of the bridges in the database, the average number of spans, the average year built, and the average life again. This is where we need to be careful with the comparisons. Directly comparing all of the bridges without considering the differences in these variables can lead to misleading results. For instance, plate girder bridges in the database have an average of over 4 spans per bridge, whereas adjacent box precast bridges average just over 1 span per bridge. Number of spans, along with the average length of the bridge, has a significant impact on costs. And that's why the report looks at all of these variables. Here, in a couple of slides, we will examine a more consistent set of bridges based on span length for a more consistent comparison. And of course, the full report examines these different variables in depth. However, for the full database results, we can use that cumulative density function again to ask the question, what is the probability that a bridge type has a capitalized cost less than $300 per square foot? And the results show that there is a 93% chance that a precast I-beam and an 88% chance that a steel rolled beam bridge have capitalized costs less than $300 per square foot. The Short Span Steel Bridge Alliance defines short spans as simple spans 140 feet or less. This table reduces the full database to bridges with lengths of 140 feet or less. It does not restrict it to simple spans, but only by the length. There is much more consistency in the average length, the average number of spans, which makes it a better comparison than the full database results. Here we're comparing bridges that are closer to each other in terms of characteristics. Here we see that the steel rolled beam bridges has the lowest capitalized costs at just over $266 per square foot, with the precast box spread bridges coming in second at about $272.50 per square foot. However, there is still the statement that all are similar with none way out of balance. Now the plate girder bridges are a little high compared to the others, but that would be expected in these short spans since they are not as economical below about 80 feet. So we go back to the original questions from owners of which type of bridge is best for life cycle costs. The precast box adjacent, the steel plate girder, the precast box spread, the precast I-beam, or the steel rolled beam bridges. And this is where we come back to that statement that all are similar with none way out of balance. The overall weighted average capitalized cost for the 5 types of bridges is $252.40 per square foot. Each bridge type average is within 14% of that weighted average. Knowing that, and that the standard deviations for the different bridge types range from $48 to over $65 per square foot, or the coefficients of variation range from 20 to 25%. What that means is that any one type bridge may be the most economical for a given bridge project. There is no one type of bridge that clearly beats out the others. So the conclusions of the life cycle cost study are: typical concrete and steel bridges are competitive on initial costs, future costs, life cycle costs, and bridge life. For any given bridge project, concrete or steel bridge types may be the most economical. Again, the preconception that concrete is always less expensive is a misconception, and that owners should consider both steel and concrete alternatives for individual bridge projects. Competition between steel and concrete bridges is healthy for the bridge industry, the owner, and the public. So if we are going to consider both steel and concrete for every bridge project, we need an easy method to produce a preliminary steel bridge design for comparison to concrete. As mentioned earlier, one of the objectives of the Short Span Steel Bridge Alliance is to develop standard, simple, rolled, beam, and plate girder bridge designs. With eSpan 140, an owner or an engineer can produce a steel bridge design in just a few minutes that meets all of the AASHTO requirements. The standard designs use common rolled beam and plate sizes and simple details for economy. The designs are for span lengths from 40 feet to 140 feet in 5-foot increments and 4 different girder spacings. The standard designs give the engineer the girder design, including fabrication details, shear stud and stiffener layouts, cross frame design, and the deck design and the end bearing design. For plate girders, the solution will produce homogeneous girders where the web and the flanges are built from 50 KSI material. It will also give what's called a hybrid solution where 70 KSI material is used in the high stress bottom flange. For rolled beam bridges, the solution gives both a lightest weight, both a lightest weight design and a limited depth design. When replacing an existing bridge, many times a smaller depth is more economical overall even though the steel weight is heavier, because with the smaller depth, existing abutments and existing approaches do not need to be changed. The AASHTO load and resistance factor design specifications have several design limits that need to be checked. The standard designs were developed to meet the Strength 1 safety design limit, the Service 2 and live load deflection serviceability limits, fatigue limits, and the constructability requirements for the construction of the bridge. For the designs, the standard AASHTO HL93 vehicular live load was applied, but there needed to be assumptions for the dead loads on the bridge due to the owner's selection of bridge materials. So down here at the bottom, it shows conservative values were assumed so that the designs will meet the different configurations that may be built. The designs assume an overhang width of 3 foot 3 inches. eSpan 140 is not really design software. It is a lookup table for the bridge characteristics. Since the designs are standardized, any 60-foot long simple span bridge with a 9-foot girder spacing would result for the lightest weight rolled beam as a W33 by 116. This table shows the matrix of standardized lightest weight rolled beam shapes based on span length and girder spacing. It also gives the diaphragm spacing for the constructability design limit. Similar tables are used for the rolled beam limited depth, or for the homogeneous plate girder, or for the hybrid plate girder designs. eSpan is a free resource. It can be found through the Short Span Steel Bridge Alliance website or directly through www.espan140.com. There are 3 steps to producing a preliminary steel bridge design. First is to create a user account. Second, input your bridge characteristics. Then eSpan will produce a solutions book with the designs. We will step through the eSpan 140, but we will not pay much attention to the details. The best way to learn what eSpan can do for you is to try it out with an example bridge or two to see how it can help you. So after creating an account for step 1, you are ready to design your bridge. You input the basic information. Here is the project name, where it's located, and then the span length. Then we define the number of traffic lanes that are on the bridge, the roadway width, the parapet width, and the overhang width. Next, we add sidewalks on there if there are any. Then we describe the skew, which is limited to a maximum of, I believe, 20 degrees. The daily traffic for fatigue checks, and the design speed. And with those simple inputs, you are now ready to view the solutions. The solutions book will provide rolled beam and/or plate girder designs according to this table. For instance, if your span is 40 feet, you will get a rolled beam solution. If the span is 100 feet, you will get a rolled beam solution, a homogeneous plate girder solution, and a hybrid plate girder solution. If they're in the right spans, you will also get corrugated steel pipe and manufacturer solutions, but we are not discussing those in this lecture. The solution book comes as a PDF file and contains the standard designs and additional information to help the owner or the engineer. We will briefly look at these here. For instance, here's an example elevation view of a homogeneous plate girder solution. And with that comes a bill of materials and camber diagram for that plate girder. This is the elevation view of a rolled beam design, a lightest weight rolled beam design. And again, with that comes a bill of materials and a camber diagram. There are also drawings for the typical details shown here for the plate girder. Simple details have been designed for easy fabrication and economy. Here are the bearing, intermediate, and connection plate stiffener details. The simple and economical bent plate or channel diaphragms are adequate for simple span bridges, and they are economical. The stud layout is actually shown on the elevation views, and the deck design is by the Ashto-empirical method. The simple elastomeric end bearings are adequate and economical for simple span steel bridges. The solutions book also presents information on durability solutions to protect against corrosion that we will discuss in detail in Lecture 4. Although not discussed in this lecture, eSpan 140 can also offer corrugated steel pipe and structural plate solutions. We will see case studies of those in Lectures 5 and 6. The Alliance also provides what are called manufacturer solutions. These are bridges produced by Alliance members that they design, fabricate, and deliver to your bridge site. We will also look at these in Lectures 5 and 6. So to conclude on this eSpan 140, it will produce a preliminary design for short span steel bridges, and it is very easy to use. As we discussed before, the best way to see if it is useful to your bridge needs is to try it with an example bridge project. So that completes Lecture 2. In Lecture 2, we looked at the costs and life cycle costs of steel and concrete bridges. We saw that both are competitive, and owners and design engineers should consider both for short span bridge projects. We learned that eSpan 140 can produce a preliminary design in a matter of minutes that allows us to compare costs with concrete bridges easily. In Lecture 3, we will continue looking at design, where we're going to look at design of multi-span bridges and see an overview of a true design and optimization software package for multi-span bridges called Simon from the National Steel Bridge Alliance that we discussed in Lecture 1. And of course, you are always welcome to go to shortspansteelbridges.org to find information on this lecture and all 6 lectures.